Consider a pair of coils, side by side, one connected to a battery and the other connected to a galvanometer. It's customary to refer to the coil connected to the power source as the primary, or input, and the other as the secondary, or output. As soon as the switch is closed in the primary and current passes through its coil, a current occurs in the secondary. When the primary switch is opened, a surge of current again registers in the secondary, but in the opposite direction. Whenever the primary switch is opened or closed, voltage is induced in the secondary circuit. The magnetic field that builds up around the primary extends into the secondary coil. Changes in the magnetic field of the primary are sensed by the nearby secondary. These changes of magnetic field intensity at the secondary induce voltage in the secondary, in accord with Faraday's law. If we place an iron core inside both coils, alignment of its magnetic domains intensifies the magnetic field within the primary. The magnetic field is concentrated in the core, which extends into the secondary, so the secondary intercepts more field change. Instead of opening and closing a switch to produce the change of magnetic field, an alternating current can power the primary. Then, the rate of magnetic field changes in the primary and in the secondary is equal to the frequency of the alternating current. Now we have a transformer, a device for increasing or decreasing voltage through electromagnetic induction. If the iron core forms a complete loop, guiding all magnetic field lines through the secondary, the transformer is more efficient. All the magnetic field lines within the primary are intercepted by the secondary. Voltages may be stepped up or stepped down with a transformer. Suppose the primary consists of one loop connected to a 1-volt alternating source. Consider the arrangement of a 1-loop secondary that intercepts all the changing magnetic field lines of the primary. Then, a voltage of 1 volt is induced in the secondary. If another loop is wrapped around the core, the induced voltage will be twice as much, in accord with Faraday's law. If the secondary has 100 times as many turns as the primary, then 100 times as much voltage will be induced. This arrangement of a greater number of turns on the secondary than on the primary makes up a step-up transformer. Stepped-up voltage may light a neon sign or operate the picture tube in a television receiver. If the secondary has fewer turns than the primary, the alternating voltage in the secondary will be lower than that in the primary. The voltage is said to be stepped down. If the secondary has half as many turns as the primary, then only half as much voltage is induced in the secondary. The relationship between primary and secondary voltages with respect to the relative number of turns is this: primary voltage over number of primary turns equals secondary voltage over number of secondary turns. You don't get something for nothing with a transformer that steps up the voltage. Energy conservation is always in effect. The transformer actually transfers energy from one coil to the other. The rate at which energy is transferred is the power. If the slight power losses due to the heating of the core are neglected, then the power going in equals the power coming out. Power is transmitted great distances at high voltages and correspondingly low currents. This reduces energy losses due to the heating of the wires. Power can be carried from power plants to cities at about 120,000 volts or more, step down to about 2,400 volts in the city, and finally step down again to 120 volts for consumer use. Power transmission uses transformers to increase voltage for long-distance transmission and decrease it before it reaches your home. Energy, then, is transformed from one system of conducting wires to another by electromagnetic induction.